Yes, thank you for this nice introduction. Yes, theoretical one. I have reduced the number of formulas and to a minimum because I think we are here for imaging, and I have reduced this to that what I think is really helpful for imaging to understand how it works. And yes, so this is also the reason why I have changed a little bit the title from Fourier and Radon transformation also to relations to MPI reconstruction. Yes, to myself, my name is Olaf Kosch. I'm from the Physikalisch-Technische Bundesanstalt. It's the German Institute for Measuring. And in Division 8, we do things for biomedical measuring, and I'm especially from Department 8.23, and this is nanoparticles. So everything about measuring is nanoparticles. And the main task that we do is characterization of nanoparticles for several, everything what's possible application. So, okay, first, yes, why we do need Fourier and Radon transformation. Yes, I think we need it for the assignment of measurement, temporal measurement in time domain, to spatial distribution by density or concentration, that we can make an image. That's simply the thing. And the famous application for Fourier is the magnetic resonance imaging, and partially, I think this we have already seen yesterday, also for MPI. And for radon transformation, it's an application. Of course, the main is computer tomography, and maybe for some kind of electron microscope also. So, yes. How does it work for MRI? There we have this fundamental equation here, which says the frequency of the movement, of the precession movement of the nucleus depends on the magnetic of the strength of the magnetic field B0, and gamma, the ferromagnetic ratio, okay, makes a decision which type of nucleus we have. But for the same type of nucleus, like protons, nitrogen, we have always the same relation. It depends only from P0. Here we have some values for optical scanners, which we can find. And this brings us already to the idea, if it depends on the strength of the magnetic field, can we, if we apply a gradient field, can we make a decision from which position the signal is coming? And so it is done in principle. We have an effective frequency which consists of a homogeneous P0 field and a gradient field. And depending from the position, we have a slightly different frequency. And the benefit of the Fourier transformation in this case is we can transform a function of time, the measurement signal, to a function of frequency. And yes, by the identification of this frequency, we can identify the locations. Further, It scales with the amplitude, so it's a linear operator, which is important for the mathematical operations. And further, yes, it's mostly not said, but the result of the Fourier transformation, the frequency components are orthogonal to each other. And what this means, I hope I can describe here in the next few minutes. Yeah. So, the good thing of the Fourier transformation is that it doesn't matter how a time signal looks, how complex, every time we can dispose it in a DC component, in an even component by this cosinus function and his harmonics, and an odd part by the sinus function and his harmonic. And this is possible or based by the orthogonality of sine and cosine function. The first is the integral over one period from minus p to p is always 0. If it's sine or cosine function, doesn't matter. And this means all AC parts are 0. And the only part which remains is the DC part that we use to determine A0. The second thing is all mixed terms with cosine and sine and different harmonics and equal harmonics, always 0. So we have not to care about them. Fine, they are gone. And the third thing is, yes, multiplying to even functions, cosinus functions, is only if the harmonic order is equal, different from 0, then it's p. And the same we have for the odd function. If we multiply to odd functions, yes, it's the same if the harmonic order is unequal, it's 0. If it is equal, then it's p. So, and this leads us to the calculation of the components. A0 I have already said, and yes, the other quotes follow from the third and the fourth rule on the page before. So let's do a simple example. I have chosen here the square leaf. It's defined as an odd function. We have this the amplitude A, and yes, due to the fact that it is an odd function, the DC part and even part is 0. So we have only to determine pk. Yes, and further, if we multiply to odd function, the product will be an even function. And due to the fact that it is the product is an even function, it's symmetrically to the origin. This means we can change the integration limit. It's enough to integrate over the positive half from 0 to p, because the other side is identical. And then we put the 2 in front of the integral. And during this time, as we can see, the function f from t is constant with a. The constant we put also in front of the integral, that we have finally only sinus k omega t in the integral. And the root function from sinus is minus cosinus, as we see here. And from the inner function, we have to put down k, and that's all. So if we put in the integration limits, for all even parts it's 0, and only for the odd parts we have this 4a divided by pk. So this is the function, and what we can see, it has a decay to the higher harmonics by 1 divided by k, which is not untypical. Maybe we know it already from the spectrum, also in MPI. And yes, it's an infinite series, and if we do the summation not until infinity, maybe this takes some time. If we do this only until n, yes, then we can see to form here a sharp edge on this position here. Yes, we need the higher harmonics. We have to add a lot of this components. And this effect we have also in the reconstruction of MPI. If we have only the lower harmonics in the reconstruction, it's impossible to get sharp contours in our result. So the higher harmonics, unfortunately, are mostly the smallest, but they are important for sharp contours. Okay, next point, radon transformation. The radon transformation is the projection. We have seen this already yesterday. We reduced the dimension by 1, and it's done by the integral over an infinite line. And for this, we have to define the integration path over this infinite line, and for all possible lines that could exist in the space. For simplicity, I do it only in 2D. And yes, we define this by 2 parameters. This is r, which is the distance to the origin, and the rotation angle alpha. And normally, we have also seen yesterday already, we have always this combination of a distance and a rotation angle. It's not enough to have 2 translations. This will not work to cover the whole space. Okay, and yes, here we have an example, and on this side we have the dependency on r, and on this side here to the rotation angle of alpha. Yes, as we had yesterday, this is named sinogram. Okay, a very simple example because the integration is in most cases not so simple. I have a circular slab here. It's defined by the circle equation. X dot by plus y equals the radius. And inside this radius, the density is 1, and outside 0. Very simple. And you will see why I have used the circular slab, because I can already say this, in this case it's independent from alpha. It doesn't matter from which direction we look, we will always get the same result. So it's enough to do this for 1 alpha, and the integration is much easier. So, but first we have to define x and y by our variables r and alpha. And s is the integration variable, so I have not said, which runs over the infinite line from minus infinity to plus. So x we get as part of vector n, which is in the direction of r. This is cosinus alpha multiplied by r. And then we have to follow the line. And this is perpendicular to n. And by this it's minus sinus alpha and s. And respectively, we can do this for y and get this expression. Okay, as I have said, it's independent from alpha, our object, so we can set alpha simply to 0, and then it simplifies also this expression to r and s, all other parts are 0. And we integrate over s, this means only the y part we have to integrate over. And this we see also here in the graphic. It's only here. And now, okay, outside the circular slab density is 0, so we can reduce our integration limits to the border of this circle. And using this circle equation here, we describe this point here of y by the circle equation, setting in the variable a, arc. Yes, and by doing this, we receive the result here in this form, the cosine function. And in principle, the sinogram looks like this function continued in that direction. Okay, so, well, what's the benefit? How we use it? For instance, how it's done in CT. We don't do an analytical integration, for instance. Nobody can do this. The aim is to find a description, how it depends. And in this case, I think it's in all imaging principles in that way that we have to set up a linear equation system. And that's all I think. And yes, for X-ray, we have the intensity defined by starting intensity multiplied by B function exponent minus line integral over rho, and rho is the absorption coefficient. So typically we have to do this numerically. So we have to discretize this, and this integral becomes infinite sum, which is defined here, dE and PE, and we have very small pieces of dI, where we define a certain rho, which is the value that we like to have. And yes, I have said we like to set up a linear equation system, and this D function is totally no-go. It's the strongest non-linearity that we know. So we have to remove this somehow. And we do this, yes, first, the starting intensity is divided to the other side. And then we take the logarithm of this equation. And yes, then this is what we measure. And this is the upper part. So it means this becomes our right hand side. And so logically, I put it to the right side. And this becomes our equation system. Rho I what is the vector that I like to calculate. And this is my geometrical description, the geometrical relationship. Therefore, also deep field matrix is used for that. So I have this equation system, but to solve this, I have to invert this. But by the inversion, I finally get the function rho for every point in my space range. So, and this means this is the So, yes. But one thing is different to the Fourier, and this is the equation system to Fourier is the equation system of Fourier is orthogonal, and this one is not. What this means, we will see later. So, relation to MPI. In MPI, we solve also an equation system, but we do this in the frequency domain, and we measure the system function and right-hand side, the u in time domain. So we have to use Fourier transformation to bring them to frequency. And equivalent, like before, by inversion, we get our Toyser concentration distribution in space. So the part of Fourier in MPI we have, but what is the role of radon transformation? First attempt I had nothing. Yes, and that's true, but only for the field-free point MPI. If we change the excitation to field-free line, we excite a whole line. This is exactly the same what we have in the radon transformation. The only thing also that we have seen in the talk of Jochen, in the frequency domain, the derived magnetization of the magnetic particle, which is dependent on the position in the offset field, in the gradient field, and to set up the equation system analytically is nobody can do this just now. Maybe someone is a genius and can do this, but the probability is very small because this M derived is a very complex function. But in time domain, in X-space MPI, we can apply the radon transformation explicitly. This means we can already, before we solve this, we have not to measure the equation system, the system matrix. We can analytically set like this. That's the difference. Okay, so the first part is done. So I go again a little bit deeper. We have here this quite a lot of time, but to show some certain points, I have to do this one second. So how MPI works. We have the nanoparticles here in the center of the magnetic field, of the derived field. It's 25 kilohertz. And they are excited with a sine signal, which has, it has a pure sine form, no harmonics, because the higher harmonics are generated by the nonlinear curve of the magnetic nanoparticles. This is our measurement signal. The analysis of MPI is based or use only this higher harmonics, and that's the reason why we can cancel out the first harmonics, the excitation. So it's decoupled. Further, if we add the gradient field, only the particles in a very small volume, the field-free point or field-free line, can generate higher harmonics. Outside the higher harmonics does not exist. The tracer or the nanoparticles generate also a signal, but not a nonlinear. And yes, due to the dry field, this field-free point or field-free line is moved, and this enables the scattering. But yes, the point that I want to go is we here in this graphic we see only the signal for the center point, where we have a symmetric excitation, which means we have exactly only the odd harmonics. In all other points, we have a mixture, a special ratio of even and odd harmonics, and it's depending on which position they are, this ratio. And they are stored in the system functions, and by this system function and this ratio between the even and the odd harmonics, we are able to reconstruct the position from where the signal of the nanoparticles was coming. Okay, but of course it's a little bit more complex. We have 3 excitations which have a similar frequency, and by this they generate this AU trajectory which moves this field-free point over the whole volume of the field, over the whole volume that we like to investigate. And this takes 21.5 milliseconds. And during this time, we collect nearly 54,000 samples in time domain. And with Fourier transformation, we convert this to nearly 27,000 complex Fourier components. Yes, and this brings me, why it is complex. This was also with Jochen a discussion yesterday, because he has said only at 25 kilohertz, it's only one curve, this magnetization, right? Okay. Yes, this is already not true. If it's really one curve, or super parametric, what we say, then it's not complex, because then it's clear we have, no delay. The magnetic particle can follow the excitation instantaneously, but it isn't in that way. There's a phase, and that's why the numbers are complex. And yes, to make a decision, especially for polar MPI, it's very helpful that these numbers are complex. Okay, so further, the system function. We measure the system function with a very small sample, which we move to all positions in the field of view. And there is a very nice tool written by Ulrich Hein, this SFU, you can find it using this address here. And with that, we can look at the spatial distribution of the absolute values and the phase. The absolute values is here coded by the brightness, and the phase by the color. Further, we can take a look at the SNR distribution in this system function, because this is also an important thing. The SNRs are calculated by the data only of the system function, not from the measurement on the right side in our experiment. And this we have to take into account. So, and now I'm at the slide where I all need these things. We see in the first row we see 3 maps of all from one tracer. It's Dynamax C30, I can say. But it's different condition. The first is only the tracer in fluid dispersion in water. The second, the tracer was uptaken by cells, and the cells are in one state. And the third one, the cells are in a different state. And all maps are different. This means in our experiments we have to choose or to measure the system function exactly in the same condition that we like to reconstruct. If they don't match, we make a mistake. It's very important. And yes, for instance, you inject this in the blood, but you have measured the system function in water. It's not the same. Because in blood, immediately you have opsonization and a lot of effects. This will change the situation. You have something different. And the other thing, you have to choose an SNR threshold, because only the frequency components which contains an essential signal, not only noise, can help you to solve the equation system. Yes, but I have already said this. This is only calculated by the system function. And yes, it's fine if you have the same amount of tracer during the system function recording and in the experiment. Then you can say, okay, then 4, for instance, is a good choice. But if the amount of tracer is different, it's smaller in the experiment, then you have to increase the SNR, because in other case you include a lot of frequency component on your right side where you have only noise. And this will only create artifacts in your solution. Yes, and this, to show you where you can find this is the SNR threshold in Parameter. Okay, I say it once more. We have to compare the spectrum of the system function of the spectrum of the state of the particles in the experiment, and they should match. It makes no sense to make a reconstruction if we do not match it. This means the decay of the absolute values should be the same. I don't mean the absolute values, only the decay, the ratio should be the same. And of course the phase also. We can check this directly in the MPI spectra or via MPX, the magnetic particle spectrum. And the second thing is the SNR values are calculated from the data of the system function, and you have to take into account how much tracer you have used during the recording of the system function and how much you probably have, you will have in the field of view. And I know that it's difficult because you inject something and 95% goes directly to the liver, and you are lucky it's not in your field of view. But how much you have in your field of view? Yeah, you have to estimate this. It's not so easy. Okay. So something about reconstruction. We have this particle distribution C, and we measure it, get a measurement signal, and together with the measured system function, always via Fourier transformation. We have to solve this equation system by minimizing this L2 problem. Everybody say it's the ill-posed problem. I don't know other problems than ill-posed. Every real measurement data and contain noise, and then you say it's ill-posed, but it says not so much about how good you can find the solution. Typically, we do this with an iterative solver like Kosch, which is also known as arithmetic reconstruction technique, but it's the same. It's only a different name. And then we get particles. But this is not the only thing that we can do. We can also use more than one. We can have 2 tracers or 1 tracer at different states. And at the same time, we can, from this measurement signal, if we have recorded the system function for both states, we can reconstruct both distributions. We get finally the distribution C1 and C2. Here we have an example. We have 2 samples of THP1 monocytes. One was treated with Cinemag P50, the other one with Cinemag C30. And yes, we put them together in the field of view, have recorded both system function for this, and then we can count the number of cells at the same time. Because we know the number, we have known the number of cells in the samples of the system function was known, and due to this, and it's a linear method, we can calculate everywhere in the field of view how many cells are there. Okay, and now the last. Yes, I have spoken about orthogonality, and yes, until now we cannot say what's the equation system of MPI, how we have to categorize this. And due to the fact that we measure it, it's not so easy. The only thing that we can do is we can idealize our system function. And for this we define the magnetization as a sine function as an infinite jump, and the derived of this is the Dirac pulse. And normally the magnetization, the derived magnetization is convoluted here, frequency space, and the convolution with the Dirac impulse is exactly 1. So finally we have in this case only the excitation. And for the cosine excitation we get this expression. It's shown in this paper of Fourier. I can really recommend this if you like to understand how MPI works in detail. Then it's mandatory that you read this paper. Yes, then we have this expression, and these are the so-called Chebyshev polynomials, and yes, they are orthogonal. In principle, they have the same properties like a Fourier system. And due to this fact, we know for an ideal system function, our equation system is also orthogonal, like Fourier. Okay, let me conclude. The equation system made totally with the Fourier transformation is orthogonal, and due, yes, this I have not taught until now. The Kosch's algorithm take a big advantage if your equation system is independent, which means every equation is independent, orthogonal to each other. Because it is done in an inner iteration, equation by equation. It optimizes the first equation, then the second, and so on. And if they are independent, if the algorithm is working on the second, it will not change the result of the first one. But if they are not orthogonal, every step changes the equation that he has handled before. And this cause, if it is independent or orthogonal, it means one iteration is enough, you have the final result. Yes, in the case of Radon transformation, it's not orthogonal, so you need a lot of iterations more. To say a number, I have written here 1,000, it can be more or less, something around this. Okay, depending on the magnetization, how strong this step is, you need few iterations in MPI, but due to the fact that if you do a color MPI two equation systems together, they are probably not orthogonal, you lose this feature. And again, you need a lot of iterations. So keep in mind, if you will go from normal MPI to color or multi-parametric MPI, you will need a lot of more, iterations more compared to this normal MPI. Okay, that's all. Thank you for your attention, and yes. Any questions? Yes.
Are they also artificial intelligence-based approaches for image reconstruction?
Yes.
And how these models look like, or is this?
Yes, they are different quite a lot.
Okay.
You have studied the literature.
Okay.
I cannot reflect this all, but some of them reduce the range where you can expect particles. Other, yes, calculate the probability. It's different. You can really find it out. Yeah, but I think 20, 15 years ago, it was also very fashion to do this in MRI with probability scans, that you scan only some lines in the K room. But as you can see, there is a big yes, it's not so well accepted by the medicines because they want to be sure. Is it really what's there?
Yeah.
That's always the question.
Yeah.
Okay, so maybe in the discussion time after the break we can continue. Okay, thanks.
Thank you, Olaf. It was a very nice overview, and in fact, in the last presentation of this meeting, I will speak about this, but from the practical point of view, without these equations. But what can happen if you neglect something from this? So I am very grateful for this background. Else now we will speak about very practical part of NPI scanning, and it will be only regarding the field-free point systems, and this is field of view. So, you've seen this image many times, so MPI principle, I hope everyone knows well after these 3 days. So we are looking for a response of superparamagnetic particles to external field and their alignment with the field due to Néel and Brownian relaxations. And in equilibrium, magnetization in the external magnetic field is described by Langevin equation. It's clear, we already spoke about this. You've already seen many versions of this image. We excite the sample, which means that we change the magnetization along the Langevin function, and we can record the signal. And of course, in presence of a static external field, particles are saturated and we record no signal there. So this is just the principle, and we can distinguish particles in the field-free point and particles which are outside of the point due to the gradient. So this is just quick repetition. We also spoke about acquisition during excitation. If we have too small amplitude of the dry field, then we are still in the linear part of the Langevin function. The magnetization doesn't reach the nonlinear part. What we receive is just sinusoid, the completely same signal, same shape of the signal as is the excitation. And the signal itself, which we monitor, will be just derivative of this, but it will be cosinus, it's the same. And the spectrum will be very simple. There will be one frequency recorded. So, and this is this is a big problem because if we filter this frequency to get rid of the excitation field, we receive nothing. Therefore, we need amplitude of the derived field big enough to obtain also the signal from parts which are non-linear. Then we obtain non-sinusoidal signal, and the spectrum, as you already seen in the previous presentation, will contain higher harmonics, which are the spectrum is calculated by Fourier transform from the signal. Okay, and now how is it related to the field of view? So we apply derived field in all three directions, and in fact the amplitude defines together with the gradient field also the field of view. So it moves the field free point in the given volume, and the size will be given also by the amplitude of the derived field, which defines how big will be the movement of the field free point in the space. So if we use smaller amplitude, we actually excite smaller volume and we receive signal from smaller part. And vice versa, if we have big amplitudes, then we can use bigger volume. But it's not so easy just to increase derived field. Well, there are of course technical problems, there are some limits, but the limits are pretty strict. In our machine, we have maximum derived field amplitude 40 millitesla, and if we use the highest gradients, we get together volume which we can scan 32 millimeters, which is barely enough for a mouse. If we want to cover a volume of a whole mouse, we either can increase derived field, but we are already at the limit what the machine allows, or we can decrease the gradients. So if the selection field will be lower, then we can excite higher, bigger volume. But of course, if we lower the gradients, we increase the volume, but also we decrease spatial resolution. Very simply, we just stretch the field of range to a bigger volume, but the data itself has still the same size. And the limit, in fact, is not the Lissajous trajectory, because it's usually dense enough, as you can see here or in 3D, but the main problem is the calibration, the system function. And there are two aspects. First is that if we lower the gradients, it might happen that we are not able to distinguish points which lie close together. So if I have 2 points, 2 samples, green and blue one, and apply a strong gradient, then of course the green one feels much higher field than the blue one. The difference of the field will be very high, so it's easy to distinguish them. However, if I have low gradient, the difference of the field which these 2 samples feel is much lower, and of course it might happen that we are not able to distinguish them in the space. And here is an example on a phantom. This is a test phantom. These are 1 millimeter holes filled with a tracer, and they are 1 millimeter apart, and you can see that it's almost impossible to distinguish them. And if you use low gradients, you can do it also in colors. Here it's clearly visible that you cannot distinguish them. This whole pack of five holes represents this one spot. These two above are just here. So you can see that lowering of the gradients leads to really low resolution of MPI image. And then, of course, the resolution itself is given by the system function. If you scan the space with 2 millimeter distances between the single scans of the calibration, of course you cannot receive better resolution than these 2 millimeters. And we are going to have problems with scanning with very dense metrics because it would be too long. And then there's one really funny mechanical problem of limited field of view. If you use a special receive coil, which we have installed in our machine, it has inner diameter 42 millimeters, but you need to scan the volume inside. You can obtain system function from cubes or rectangular shape only, and mechanically you cannot go to the borders because the sample has also the test tube around and so on. So in fact you are limited to 24 millimeters in this direction, even if you have 42 diameter of the coil. So yes.
But you have the new version of Paravision, not as better with the 60 with you. Because there is also the possibility that you measure the system function not by moving the robot. You can measure the system function by switching your offsets via the focus fields.
I will speak about this.
Okay.
You are right. So, but you really can obtain the system function only from a small volume here. So, what can we do with it? Field of view can be enlarged. First approach is so-called table move, which we started many years ago, and then there's the approach with focused fields, when you use another magnetic field which just shift your field of view out. So you just measure one system function from the center, and then during scanning of your animal you can shift the whole volume somewhere else and use the same system function for these parts. However, back to the table move, it's very simple. We scan on this phantom one image, then we move the sample or the mouse, scan it again, and then scan it again, and then we just put it together and we have nice image. Here it is over with the photograph of the phantom. We already wrote a simple software for this which enables to put together images, but of course if you manually move the animal or the sample, then you have to add all the parameters manually here, because there is no connection between the measurement and the software. So it's not very practical. And we started with a small carriage moved by the robot. It was built from Lego, so it's very useful. And then we printed out some carriages which can be used for for animal beds, and it can be moved by the robot, so you have really precise position in the magnet. Another possibility is the use of the focus fields. So you really measure, as Olaf said, system function from the center, and then you apply focus fields, and when you scan the mouse, you can scan the mouse from different positions due to movement of the field of view in the space. So it's here on a mouse phantom. This is put together and you can receive a much bigger field of view. So, about this will speak my colleague Martin. So let me just conclude this. Basic field of view of the FFP system is rather small, but just it is. It can be enlarged by increasing the derive field or decreasing selection field, but in this case you lose something. Derive field is often limited by hardware. Lower selection fields leads to lower resolution, and then there is the table move method or focus field coils, which enable moving either the sample or the scanning area in the space. Field of view also itself is limited by the calibration method, therefore you really need, if you want to scan bigger areas, you really need either focus field or table move method. So at this point I hand over this to Martin. If you have any questions at this point, just ask. Otherwise we will continue and Martin will speak more about the multi-patch reconstruction test.
Nice to meet you. My name is Martin. I'm here from Center of the Advanced Preclinical Imaging from Charles University. I will now talk about reconstruction approaches to multi-patch data from MPI that you can acquire through the MPI. So let's start. My concept of my presentation is that there's a lot of approaches how to combine these separate volume. There's some AI approaches. There are also some sophisticated algorithm, but I will talk more about two the most already implemented as usable packages or some application. One of them is ours, and one of them is from colleagues from Hamburg. But let's start it. So why we want to somehow reconstruct the data? Because we have something that occurs in every patch or the separate volume, and that is border artifacts and some artifacts that occurs on the borders of the wall volume. So we want to get rid of this and have nice images. First approach is patchwise reconstruction, that we take the volume and set up them like this, and then we can just it's the simplest approach. Set up them like Lego, and then have a big volume, but it will not suppress our border artifacts. So we will need some overlapping systematrics. Overlapping patches to to suppress the border artifacts and have nice images. To the overlapping area, we can apply some really, it's the most straightforward method that you will, how to say, you will think if you want match some data, you will just to cut it off. Just if I have some artifact and have some nice signal in the center, so I can just imagine that everything else is noise and just the cut of the border. So I have nice clean volume. But there is some like losing of information that can be useful. But so we can try to average them. Also, but if we have a different, if we don't have, if we have variability in the noise on the borders, so it will just average the artifact, and then we have like still noisy images, and I will show later. And we have also applied some function. We can apply whatever you imagine to just to suppress these edges. Okay, so it's I say it's very. I just forget one thing that pitchwise reconstructions need to be pre-reconstructed. So we will get a bunch of volumes separately and then merge them together as pre-process. Like it's not the reconstructions itself; it's just pre-processing already reconstructed volume of from MPI. So as I say, it's very simple. It's easy to implement because it's just moving matrices with some overlapping area, and so you can do it in your laboratory. There is also some disadvantage. For better images, you will need bigger overlap because then you will obtain less border artifacts, more and more useful signal. So you can have more metrics, but it can be just using just one metric, so it's disadvantage, but already not. So also I say you will lose some useful signal that is corrupted by the border artifacts. Then we have, as I say, you can do it in your laboratory. We have our own, which is called WOMPI. This is the program that those who already have the hands-on. I was merging like and overlay on the end of the hands-on, like the black application. It was contemplated. It has just 4 steps. It loads data, then you will choose which one, which function you want to apply on the overlapping areas, and then just run the reconstruction and save it as a DCM. Unfortunately, it works only on data from Broker that we have in our lab. So, and it's available on GitHub, so if you want it, you can download it, we will be happy. But it's still in development. Okay. So then, so now there is the image that when you apply the average on the overlapping area, you can still see there is a lot of distortion from noise from the border artifacts, or you can use which is Gaussian with that is suppressed and also have like zeros and on the borders, but the images be kind of like fuzzy and can be like you really lose the information. There is the MRI of same phantom, and there is volume from the merger. Second approach, as I said, is joint reconstruction. It's similar to normal reconstruction that already we speak here. We already speak here as how to say is really same as by reconstruction in MPI, but we will just take the system metrics in one system metrics, like we want to reconstruct, and then also the measure signal, and then use some iterative solver to solve this system of linear equation. So there is no pre-process. This is not pre-processing algorithm. It's already, and you get already the whole volume reconstructed without the border artifacts. There will be still on the first layer and last layer, because there still be some border artifacts, but in the middle of you will get the nice clean images. As I say, also there's a big advantage because you can use it with no overlapping patches, so your measurement can be quicker. You can use system matrices and this. Also, there is a big community that improved this. Also implement this algorithm. I think it's guys from Hamburg. Also, there is a lot disadvantage because it has iterative solver, so you need to set up parameters, but it can be easily solved by some optimization algorithm like ADAM or something like that. Also, it's computer challenging because we don't solve just one system matrix with one measured signal. We have whole bunch of system metrics in one matrix and then solve it. So it's more linear equation than normally. But it's also can be solved, but then, or as I say, the community still try to improve this packages. So we have on this international conference that in the case of MPI, they introduced some GPR accelerated for the multi-patch reconstruction. So they trying to improve these packages. They're still doing some new function. You can find it here. It's this one package is just for reconstruction for multi-patch, and also like just simple system metrics. They also have some simulation packages and file packages, and it's everything written in Julia. So it's need a little dive to it and get used to it. I tried and I failed. So if anybody already tried and success, please contact me. And from this point, it's everything. Thanks for your attention. If anybody has any question, I'm here. Has anybody any questions? No? Out.
I want
Yes.
to make this reconstruction. Which kind of, your instrument, which kind of data is giving you? So you are working on the final DICOM file, or you're working on the voltage file, or whatever?
Yeah, so the WOMPI works with already reconstructed data from Paravision, I guess, and then we take the raws. The WOMPI take the raw.
No, already reconstructed data as 2D seg files. It's the format of Bruker data.
So you're
it
basically
takes
working
just reconstructed images and then merges it through.
So you are working already on pixel intensities.
Mm-hmm.
Yep.
Thank you.
Any more? Okay, thanks. So then have a great coffee break, and it's all for me.
We ended a little bit earlier, but I suppose that it doesn't matter because the last presentation, I hope that it will be a rather discussion about the problems which I want to write here. So enjoy the coffee break, and I don't know, in 15 minutes we can continue. Okay, so this is the last presentation of this workshop, And I would like you to participate on it. If you have any questions, things to discuss, just raise your hand, and we have quite a lot of time for it. I will introduce it by speaking about limits, pitfalls, and artifacts. I'm sorry that David Rees is not here, because I will speak only about field-free point systems, and I really don't know and don't dare to guess what's happening on the side of field-free line systems. So, first starting, what's the future of MPI? So far it's really nice toy for physicists. It's an interesting tool for preclinical imaging, but what about the clinical practice? And, well, I just remind you the history. 2001 first MPI image, 2005 nice paper about imaging using MPI, 2008 fast 2D encoded magnetic particle imaging, which made it really available for preclinical imaging. Now it's 2025. If we compare it for MRI, it's quite interesting. First image was presented in 1973. 1977 was first whole body MRI system presented and the first human image. And in 1983, MRI scanners were commercially available. This is Siemens magneton system. So it took 10 years from first image to commercially available clinical scanner. Even here, behind the Iron Curtain, the first imager was installed in 1987. So, as you probably understand, I am quite skeptical about clinical usage of MPI. And still there is no clinical scanner after 25 years of exploring of this quite interesting method. There are visions how it could work, but there is a lot of problems. Limited field of view, low resolution. Currently, field of view, as we spoke about this during the morning, it hardly covers a whole mouse, not speaking about the whole human. Increasing field of view leads to loss of resolution, or with some problems, patch measurement and so on. We can use lower gradients, but of course we use resolution, etc. We spoke about this quite a lot. And it's for me extremely hard to imagine that field-free point method would be used for clinical imaging as a whole body system. There are attempts to do it like handheld machine to scan just part of the body. It might be possible, but as a whole body system, it's really very difficult. Calibration to bigger metrics, well, it's impossible, of course. Hardware. At one conference, I saw a nice calculation when they just tried theoretically to expand current MPI systems so that they can hold a human body, and ended up with some megawatts of energy necessary to run it. So you would really need a power plant for it. Of course, there might be some technical advancement and other technologies and so on. So, and that's really pity that David Chris is not here to speak about field-free line systems, which it might be possible. But if we use field-free line systems, we lose the advantage of the speed, which is very nice in the case of field-free point systems. So, MPI problems. Racer. Still, it's a big problem for MPI. Physical problems related to nail relaxation and Brownian relaxation and frequency which we use for excitation. We already spoke about this. The generated signal in the core is just an integral of such a horrible equation, where of course is core sensitivity. If we neglect this, we can do some calculations, and it will be a derivative of magnetization, which depends on the excitation field. But if we recalculate this, we get here that the signal depends on the change of excitation field. Therefore, relaxation times are crucial. We cannot just slow acquisition, because if we slow excitation, then we lose the signal. So this is the problem which everyone solves when developing the nanoparticles. Nanoparticle size, we don't speak about this too much, but it's rather paradoxical, because actually if you need better resolution, you need bigger particles. So the bigger particles, the better resolution, because the resolution is not done by the size of the particle. It's in terms of nanometers, and resolution is in our case in millimeters, or maybe tenths of millimeters. So how this happens? Magnetization of the nanoparticle is given by this equation, and mu, the magnetic moment, is crucial here. And the core size affects the curve through mu. So if we have small particles, we have very flat magnetization curve. If we have big particles, we have nice steep curve. And as we already spoke about this, if we have broad linear path here, then we obtain that signal. There was, in this book was published this interesting table. This is diameter of the particles, or of the cores of particles, saturation, field, and resolution. It looks horribly because this is really big nanoparticles which we really need for imaging, but this is a theoretical value. In real life, we can reach higher resolution because we are detecting a number of higher harmonics. So this is not valid as it is presented here, but still you should keep in mind that very small particles will have better resolution because their magnetization curve will be very flat. Particles which we use should have narrow size distribution. They should be homogeneous, otherwise we obtain signals which are hard to handle. Here is just an example. if we have particles with nice magnetization curve, we obtain good signal, nice spectrum. If there is size distribution, then there's some contribution from particles which have different magnetization curve. Of course, they respond differently. It mixes in the spectrum and so on. So really narrow size distribution is crucial. And of course, the broad size distribution introduces some ambiguity into the signal, because you don't obtain separate signals for separate different particles in your sample, you obtain just some of it.
I thought that the harmonics were like multiples of the excitation signal. So how would different particle sizes influence the harmonics? I would say that they all would overlap theoretically, right?
Yes. Well, in fact, you obtain some of the signals. That's it. And you don't know how to separate it. So. Signal decoding, another big issue in MPI. We already spoke about this. We measure the signal, and now we measure the signal from the whole volume, and now we need the calibration data, and in fact split our signal into the metrics of the calibration data of the system metrics to find out which components are present here. And from this, from the linear coefficients, we can calculate the concentration and distribution of the nanoparticles in the sample. What I see here as a big problem is that system function, it's really a matrix of spectra, and really very big matrix. If we use matrix like this, which is for resolution, which doesn't represent a big matrix in terms of resolution, we have 10,000 spectra in the system matrix, and we are fitting this into our data, and there's too many degrees of freedom. And if you calculate also with some noise, then you might be in big trouble just mathematically. Fitting procedure. This is quite tricky, and we still battle with this. The fitting procedure or fitting parameters should be tailored to the measured time. Olaf already mentioned that range of frequencies of number of higher harmonics is crucial, because it doesn't make sense to include the noise here, because it spoils the fitting. And then there's regularization parameter, which is, this is extremely hard, and you really keep in mind that it's not the same for different samples or different matrices. I just try to explain it on an example. It's not exactly what we are speaking here about, but it's the similar problem. If we have points like this, and we know that it's sinusoidal and wants to fit a sinusoid function through it, through some iteration method, then we use the sum of deviations as a criterion. And once the sum of deviations is low enough, then we stop iterations and we are happy. If we use bigger set of data, we actually can reach same sum of differences, but only with better fitting function. So we have same error or sum of errors here, and at the first sight you can see that this is much better fitted than this one. And so if you use different matrices, then you should use different regularization parameter. And what we found out, well, in fact, by just practical testing, if we have lower matrices, we should have used stricter rules for fitting, which means lower regularization parameter. And during the first hands-on, which we did here, I didn't realize this. I realized it at night when I was thinking why we received so bad image. And this was this case. We had a sample which had 2 millimeters. We measured matrix, system matrix 5 times 5 with 2 millimeter resolution, put it into the center then and measured the image, and we should have received just one bright pixel there. But what we saw was dispersion of the data around. So it looked like this. The next day, when I thought about this, I changed the regularization parameter and measured and recalculated the same data and found out, well, it's correct. So the fitting procedure or the iteration is very sensitive to any errors and to the setting of regularization parameter. Olaf already mentioned this, we showed there noise, frequencies, and regularization parameter. So if you, yes?
Let me add, yes, it's really crucial with this regularization, because also if you use the same regularization and you cut off some of the lower frequency, and the regularization is normalized to the power of the equation, and you depend the most energy is in the lower frequency.
Mm-hmm.
And if you cut out the regularization will work completely different kind of conversions. Then if you include this higher frequency component, then of course the regularization is much stronger. It's the same number, but due to the normalization to the energy, it works completely.
Yeah.
And this makes it really very complicated.
So, well, so far we were lucky when we are preparing some experiments. It means if we really have an experiment on many mice and so on, just to carefully prepare everything, try the possibilities, different concentrations on phantom, run the experiments, set everything, and we pray that everything's okay. Well, so far it works. And then you should keep the parameters similar if there are no big differences in for example, applications and so on. So, and we are going to artifacts, or if anything goes wrong, you already experienced this also during the hands-on. So, first check your hands. If you work in vivo with animals, you should ask if the probe is applied correctly. This is usually the most common mistake. Then check whether the sample or the animal is really in the magnet where it should be. I remember quite funny experience. It was with MRI when I first saw high field MRI for animals. We tried this on an orange, which we put inside, and made some localizer, it was nice, and then we made some further sequences and there was no signal. It was very simple because of the vibrations of the gradient system. The orange rolled out, so check the position. Usually it's one very easy mistake and easy to correct. Then you should check your tracer, because not all the tracers are stable in time. If there is some sedimentation, you might reach a situation that there's some hysteresis and different magnetization curve and so on. And check the machine at last if something is wrong. So, and of course, if there are some problems, you should run quality control regularly, so you can mention some problems with the machine. We are running it at least once in a month with a known sample, which we do calibration, simple calibration, which we do during the hands-on, and then place the sample in different positions and check the signal to noise. It's quite simple procedure, but it's worthwhile. Check spectra of your probe. This is nice. This is somewhat worse. We are missing here higher frequencies. And of course, you can use the procedure for quality control to check your probe. So you can see in this case, this probe behaves, it's much worse. The signal is dispersed, probably due to some size dispersion in the sample or aggregation. And if you reach during your quality control something like that, then you know that something really wrong with the probe. So sometimes, if it is like this, it might help to recalibrate. So do measure another system metrics, because if there's small aggregation and if the sample is still stable, then recalibration might help. Well, and then check the machine if everything else fails. Well, this is how the machine looks like during some reparations, but we don't do this on our own, but small repairs we do by ourselves. These are not very old images, this is from yesterday. And of course, we are not going into the electronics and stuff like this, but if there is what happened yesterday, if there's some leak of water because the magnet is cooled by water, we can fix it. And I recommend you, if you are going to buy an MPI system, to have some handyman around who can help with basic things, because service from Bruker is professional, but they won't come in 10 minutes. They won't come in 10 days. So count with this. We spoke here about border artifacts. Well, this is a very interesting thing. There are papers about this, but basically what's happening here, why we have on the border some strange signal, is that we are choosing some volume of interest, but well, in fact there might be some signal from around, we cannot avoid this. But this signal is not well defined because we don't know how strong is the gradient field there. There will be for sure some, but it's stored, and the same is for the dry field. Here is one example of it. This is the phantom which you already saw. So there are some, it mimics some intestine, liver, and so on. It's here in 3D reconstruction in different positions. So if it's not well visible, but from this side here is the sample, and here is artificial signal on the border. The easiest way how to cope with it, well, here are some papers which mention this and speak about this and how to reduce this artifact, but the easiest way is just to cut it. If you have single volume, it's easy, you can cut it and just take the part which you are interested in. But of course, if you do multi-patch imaging, it's not so easy as Martin presented here. There are many different approaches how to cope with it. And here is a nice example. If how it looks here, I will show it from the right side. Here is single patch of MPI, so we are scanning just small area here. You can see a nice signal from the liver and from the spleen. This is multi-patch obtained with 2 patches, that's also good. But here is localization of image and 18 patches from MPI with no suppression of the border artifact. So actually you see here just only the artifacts. Here it is without the MRI. So there was 18 patches, it means 3 times 3 times 2, so you can see 3 overlapping patches here, so it multiplies this artifact. So study your artifacts if you want to avoid them. And this is the software which Martin wrote, and part of you already saw it during the hands-on, and the last group will see it again. So, to summarize it, why MPI? This is against. It's still rather experimental machine, at least the field 3-point machines. So, and there you encounter a lot of problems on many sides, tracers, hardware, reconstructions. There are several principal problems like long calibration, small field of view, low spatial resolution, and artifacts. On the other hand, to be somewhat optimistic, it produces nice images which are comparable to PET or SPECT in terms of just looking at it, but without radiation. You use a tracer which you can image, and you see just the tracer with no background. Speed. FFP systems are capable to get really images really very fast, and so you can follow really very quick processes and distribution of nanoparticles in vivo. And what seems to me very important for future, and hopefully even for human medicine, is the possibility to combine this focus hyperthermic treatment, because the gradients which creates the field 3-point enables you to exactly focus hyperthermia, because you can heat just this spot and nothing else. And actually, I don't know if it is experimental medicine machine. Is it advantage or disadvantage? For me, it's an advantage. It's a nice tool which is potentially very interesting. As I am a physicist, it's a nice story, and but I still think that it remains as a practical tool. And if you run one, I think that, as I see you here, it would be great to have this group running an NPI system, because here are chemists, physicists, physicians, biologists, also some engineers. It's perfect for running an NPI system. And there's a lot of places where you can do research on NPI, and a lot of teams regarding still data acquisition, nanoparticle development, and applications. So, thank you for your attention. These are not from NPI. So, I don't know, if you want to discuss about this theme, I think that it's a really important issue. What's the future of NPI? There are no questions, everything's clear.
An alternative might be not to compare it with whole body systems like MRI or CT, but with limited applications like ultrasound. We use ultrasound in the clinic all the time, but for specific parts of the body. So
Yes.
NPI might have the same role.
That's possible. I saw on one conference a concept of, it looked like a big probe from ultrasound, like handheld system which you can place somewhere. And as I mentioned, I think it might be good for if you combine it really with hypothermia. Otherwise, I think that ultrasound in clinics probably replaces just imaging. But combination with some treatment, this is, I think, the way where it will go. Well, we will see.
But
Yes.
I think what we can conclude from what we saw these 3 days, that there are different aspects to improve: the technical aspect, engineering aspect, of course, everything related to it, and then also the nanoparticles probably, because we didn't, so I think all of them should meet at one point
Exactly.
to improve everything, and this is what we need to discuss maybe.
Yeah, and that's why I think that you are from the part of research of nanoparticles.
Right.
This is what's really necessary. Then biologists are necessary to find out some applications. Yeah, it's a really machine which has the power to connect people from different areas.
Maybe also can be used as a Spiro set for some part of the body where it's already good characterized by MRI or some other imaging technique, and then we know a specific location of the problem, and then we apply just to get some additional information about metabolic activity or something else.
Well, if you speak about MRI, if there's a patient who cannot go into MRI probably because of some implants, it will be the same here.
Yeah,
Maybe even worse.
Yeah, but for those who can,
Yeah, but-
if you have information about the structure of the tumor or some borders of the tumor, and you want to expect additional response to therapy or something else, and you know exact localization, you can apply this technique to maybe get additional information to how they are responding to therapy.
Mm-hmm. And it reminds me one point which mentioned David Rees yesterday, and I was really very surprised by this, that they are capable of detecting of hemosiderin. This seems to me that it might be application which would be very useful. Because so far it's very hard to do this. You can see some bleeding or something like that on CT or MRI, which takes quite a long time, but if there is a possibility to replace in these cases CT by something without X-ray, it would be good application.
But as a physician, I do not agree with that because you can use CT in less than 1 minute and you know the diagnosis if there is bleeding or not. And using this technique, you will need to wait more than just 30 seconds.
I think that the field-free line system in tenths of time is comparable. Actually, the reconstruction and the scanning is the same.
Yeah, but maybe the cost
But,
of CT
well, so
in
far we
cameras-
don't have a human-sized scanner even in field-free line, so it's just theoretical question. Okay, before we
Another question.
yes.
If I'm not mistaken, yesterday the two commercial speakers from Magnetic Insight and Brugger said that the scanning frequencies are fixed. You don't simply change the kilohertz in any way you want, which in turn limits the nanoparticles. How big of a problem is that for development?
I actually don't know, but the colleagues of mine from the Faculty of Mathematics and Physics here in Prague, during COVID, when our machine was broken and we were not able to get it fixed due to closure of the border, they built their own spectrometer, so without the gradients, and they can change their frequency in big range, and it's very interesting for testing and tuning of the nanoparticles for MPI, because they really have spectra at different frequencies. They can find what's possible, where the nanoparticles work best, and so on. So, and of course they can, due to this, they can measure relaxation nails, relaxation times, and derive Brownian relaxation and so on. So for development of nanoparticles, this is perfect, but I actually don't know how difficult it could be to build a machine with different frequencies. I don't know if Olaf, do you have any idea?
I hear the new scanner that Brugger developed actually. You can have two frequencies, 25 and the lower and half 12. But not continuously, only this two. I think at lower frequencies are interesting if you like to investigate something with Brownian relaxation. I think this is interesting for elastography. Yeah, because at 25 kilohertz we have mainly the effect from the severe relaxation. The Brownian would be calcium.
So, any other questions? Well, before we conclude this, I have one question, and there was a proposal for the last hands-on. If you agree, we can start once we finish lecture or this session here, and we can
go directly to the lab and go for a lunch afterwards if you agree. Is it okay with you? I don't know. Yeah. So, Luděk, do you want to say something at the end?
Thank you for coming to Prague. I think that it was the first connection of such people, except of international workshops on NPI. And I believe that we can work on it further with nexMPI in next 3 years, that the cost action will take, and I hope that you enjoyed not only the presentations, but also our capital, Prague. The weather was quite nice, and I hope that we will see next time at another actions. Thank you.
Thank you.